Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference, but now we are in the part of statistical inference. Okay, so you can recall that in the last lecture we constructed the confidence interval for the mean under the normal mu sigma square population when sigma square was known to us, and I had given you all the steps in detail that how are we trying to construct the confidence interval. Now, in this lecture I will try to take the second case when sigma square is unknown to us. Actually, that will be a more realistic situation in most of the real life cases, that you are trying to estimate a parameter and the parameters are actually unknown to us. So, if there are two parameters, both the parameters are usually going to be unknown to us. So, now we want to estimate the confidence interval for mu when sigma square is unknown to us. So, one simple option is this, that we can estimate the sigma square and we can replace it in the place of sigma square, and based on that we have to construct a Whittle quantity which is depending on the parameter and the random variable, but the distribution of this quantity is independent of the parameter. So, now the question is, how are we going to do it? Well, do you remember the sampling distributions, and do you remember that we had done 3 sampling distribution, chi-square, t and f. Now, in this lecture I am going to employ the properties of t distribution to construct the confidence interval for mu when sigma square is unknown. Right. Suppose you have a sample from normal mu sigma square. Now, you are trying to estimate the sigma square also. So, do not you think that we should also construct a confidence interval for the sigma square? Yes, we will do it in this lecture, and for that we will try to use the properties of chi-square distribution. So, let us begin our lecture and try to find out the confidence interval, but remember one thing, the steps, the procedure, the methodologies, they are going to be the same as we have done in the last lecture. Right. So, I will not be repeating the same steps again and again in this lecture. If you have any doubt or problem, my sincere suggestion is that you please try to revise the earlier lecture first and then you watch this lecture. So, we begin our lecture. Okay. So, now let x1, x2, xn be a random sample from normal distribution, normal mu sigma square, where sigma square is now unknown to us. So, let this x1, x2, xn be indicated by x underscore, just for the sake of simplicity. And now you know that how to estimate the parameters mu and sigma square as a point estimates. So, the mu can be estimated by the sample mean, that is x bar is equal to 1 upon n summation I goes from 1 to n xi, and the variance can be estimated by 1 upon n minus 1 summation I goes from 1 to n xi minus x bar whole square. And yeah, means if you remember, other form is 1 upon n summation I goes from 1 to n say xi minus x bar whole square. Right. So, these are the point estimates. Right. Now, we are more interested in finding out the interval estimates for mu and sigma square. So, now first we have to construct a Whittle quantity. Right. So, now this is the main task. Once you complete this task, after that the entire story becomes very simple, and it becomes very simple to obtain the confidence interval. Right. So, now can you recall the t distribution? It was like this, that if x1, x2, xn, that is a random sample from normal mu sigma square, then x bar follows normal mu sigma square divided by n, and from the chi-square distribution, do you recall that n minus 1 s square upon sigma square will follow a chi-square distribution with n minus 1 degrees of freedom. And we also have done one result while discussing the distributional properties of the sample mean in an earlier lecture, that both x bar and n minus 1 s square upon sigma square are independently distributed. So, now we can define the pivotal quantity as say x bar minus mu divided by sigma by root n, right, and divided by square root of n minus 1 s square sigma square divided by degrees of freedom n minus 1. Right. So, if you try to simplify it, this will come out to be square root of n x bar minus mu divided by s, which is actually x bar minus mu divided by s by root n, right. So, this is a statistics which is going to follow a t distribution with n minus 1 degrees of freedom. Now, I do not need to repeat it, that I will simply refer you to t distribution where we have discussed all these things. So, now this is going to be a pivotal quantity. Why? Because g x theta mu sigma square, that is depending upon mu sigma square x1 x2 xn, but this quantity square root of n x bar minus mu, although this is a function of here mu, but the probability distribution of this quantity is independent of any of the unknown parameter like mu, and it is depending only on the degrees of freedom n minus 1. So, now we can use this pivotal quantity to construct the confidence interval. Now, once you know this thing, then after that the life becomes very systematic and simple, right. If you want to find out the two-sided confidence interval, you simply have to see here that this is the pivotal quantity which is lying between minus t alpha by 2 n minus 1 and plus t alpha by 2 with n minus 1 degrees of freedom. And the probability of this event is equal to 1 minus alpha according to the definition of confidence interval, right. So, now if you simply try to solve it exactly in the same way as we did in the case of normal distribution, you can obtain the lower limit and upper limit here like this, right. So, where this value t alpha by 2 n minus 1 can be obtained from the probability tables of t distribution, or you can also obtain it directly from the software also nowadays, right. This capital X bar can be obtained on the basis of sample, capital S can be obtained, that is the standard error can be obtained by using the observation x1, x2, xn. So, all these theta hat u and theta hat L which are obtained here, they can be computed very easily. So, this is you here theta hat u and this is here theta hat L. So, I can write down here that 101 minus alpha % confidence interval for mu in such a case is obtained as theta hat L. This is the lower limit of the interval which is here like this x bar minus t alpha by 2 n minus 1 s by root n, and the upper limit is theta hat u which is dependent on x1, x2, xn. This is given by x bar plus t alpha by 2 n minus 1 s by root n. Exactly on the same way, if you try to see, the structure is very much similar to what you have obtained in the case of normal distribution, right. The structure is like that. You are just using here t alpha by 2 in place of z alpha by 2, and you are using here s in place of sigma 0, right. So, now I can say that this is the confidence interval in the case when sigma square is unknown to us, and in case if you try to judge this confidence interval on the basis of the length of the confidence interval, then one can very easily show that the interval what we have obtained, this is the shortest confidence interval, right. So, that means this is a good confidence interval, and if you try to see here how it will look like, right. So, here you can see that we are trying to take the value of this area to be alpha by 2 on the left hand side and right hand side of the t distribution. So, this is actually x square root of n x bar minus mu divided by s. This is the distribution of this quantity, this is the curve of this quantity, right. And now, in case if you try to translate it, the confidence interval will look like here. This is here the lower limit whose value is x bar minus t alpha by 2 n minus 1 s by root n, and this is here the upper limit whose value here is x bar plus t alpha by 2 n minus 1 s by root n, right. So, this is how this two-sided confidence interval will look like. Two-sided means because the confidence limits are on both the sides, and the middle part, this area is 1 minus alpha, right. Okay. And in case if you want to find out the one-sided confidence interval, so the one-sided upper confidence interval can be obtained just by solving exactly in the same way as we have done in the case of normal distribution when sigma square is known to us. So, we can write down here probability that square root of n x bar minus mu upon s is less than equal to t alpha n minus 1. Now, it will be say here t alpha, right, because the entire area is only alpha. So, if you try to solve it simply, this limit will come out to be x bar minus t alpha at n minus 1 degrees of freedom capital S by root n, and this is less than or equal to mu, and this probability is equal to 1 minus alpha. So, the 101 minus alpha % one-sided upper confidence interval for mu is obtained here like this: x bar minus t alpha with n minus 1 degrees of freedom into S by root n to infinity, right. And similarly, you can also obtain the one-sided lower confidence interval by solving this condition, that probability that square root of n x bar minus mu upon S is greater than equal to t alpha with n minus 1 degrees of freedom, and this probability is equal to 1 minus alpha. And if you simply try to solve it, you get here mu is greater than or equal to x bar plus t alpha n minus 1 S by root n. Right. So, the 101 minus alpha % one-sided lower confidence interval for mu is obtained as the region between minus infinity to x bar plus t alpha with n minus 1 degrees of freedom into S by root n. So, you can see here this is exactly on the same line as you did in the last lecture. That is what I had requested you in the beginning, that if you have done that lecture, then you will understand it very easily, right. So, now as we have obtained the sample size in the case of when sigma square was known. So, similarly, in this case also we can obtain the sample size, right. So, here since x bar is being used to estimate the mu, so some of the values of x bar will be less than mu, some values will be more than mu. So, the absolute error between x bar and mu can be expressed by here quantity E. So, we are now saying that we would like to find out the value of sample size, right, and we would like to find out the sample size in such a way such that error is less than or equal to t alpha by 2 n minus 1 S by root n, right, with confidence coefficient 101 minus alpha %. So, in such situation where the sample size can be controlled, we can choose the value of small, and that is the sample size, so that 101 minus alpha % confidence interval, or at least we are 101 minus alpha % confident that the error is in the estimating the value of parameter mu is less than a specified bound on the error E, which is given here, right. So, now the appropriate sample size can be found by solving the equation that t alpha by 2 n minus 1 into S by root n is equal to capital E, and this will give us the value of here n like this: t alpha by 2 n minus 1 into S divided by E whole square, right. So, from there you can obtain the optimum value of n. But you have to just be careful in the case of this case when sigma square is unknown and you are using the t distribution. In this case, suppose if there is a condition that your sample size is more than 30 and sigma square is unknown. So, do you remember that we had a good discussion in understanding that when the degrees of freedom in the t distribution becomes more than 30, then the curve of t distribution and the curve of normal distribution, they becomes almost the same. So, in such a cases, either you are trying to find the critical values from t distribution or normal distribution, they are going to be the same, right. So, when we are trying to consider the situation where your sample size is large, say more than 30, and sigma square is unknown, then in that case you can also use the critical values z alpha by 2 in place of the critical values t alpha by 2. Right. Why I am calling them critical values, that will be clear to you when we try to start the discussion on the Kirchhoff hypothesis in the next lecture. But at this moment you can just assume that they are called as critical values. Right. So, the moral of the story is whenever you have the sample size more than 30, then you can use either the normal distribution or the t distribution, and both are going to give you the same result, right. Although in the case when sigma square is unknown, you are going to estimate it on the basis of the sample, but still both the confidence interval are going to be almost the same, right. So, in case if n is reasonably large, say more than 30, then even we can handle the case of unknown variance directly by the last sample size situation, right. So, when n is greater than 30 and sigma square is unknown, a reasonable assumption is that the underlying distribution is normal instead of here t, right. So, and you see, in particularly in data sciences, you can expect that usually the sample size is expected to be definitely more than 30, right. So, that is the reason that this case becomes they are more popular, and that is the reason you will see that in the software also people are more interested in developing a software for the case when sigma square is unknown to us, because that is more practical situation, right. So, in many population in practice they are well approximated by the normal distribution. So, this assumption will lead to the confidence interval procedures which are of wide applicability, right. So, they are easy to use, so they become more popular, so they are more convenient, people can use them easily, people can find them easily, right. And in fact, if there is some moderate departure from the normality, that may be possible, but that is going to have very little effect on the validity of the confidence interval. So, you do not have to worry for those things, right. So, in such a case when your n is greater than 30 and your sigma square is unknown, you can redefine the same confidence interval like this: x bar minus z alpha by 2 s by root n to x bar plus z alpha by 2 s by root n. So, instead of using here the t values, we are going to use here the normal values, right. And in case if you think that the assumption of normality is really going to be not satisfied and the data is not really coming from normal distribution, then if you find it, or even if you are finding it difficult to verify that data is coming from any given distribution, then under those situation my suggestion will be that you can use the non-parametric statistical procedures, which do not require the information on the underlying distribution. Well, I am not going to discuss here, but surely I can give you this idea. Once you know, once you have done so many topics, you can do now non-parametric inference yourself without any problem, right. And I assure you that is not going to be difficult. Okay, so now if you try to get convinced here, I have just constructed some graphics. So, you can see here this is the curve with t distribution with 1 degrees of freedom, this black color is the curve for the t distribution with 2 degrees of freedom, and then this green curve is the t distribution curve with 10 degrees of freedom, and you can see here the degrees of freedom are increasing and then height of t distribution is increasing, and here in this red color this is the normal 0 1. So, you can see here at t equal to 10 they are very close, but if you try to increase it to n equal to 30, that means 30 degrees of freedom, then normal 0 1 and t 30 they will become identical, right. So, both distribution are the same. Now, if you want to know this value somewhere here or somewhere here on the left hand side of the curve, then either you try to use the normal distribution or t distribution with say 30 degrees of freedom or more than 30 degrees of freedom, that will not make any difference, right. So, now let me try to take an example and try to compute these confidence interval manually and on the R software also. So, I am going to take the same example which I considered in the last lecture. The only difference is that there I assume the sigma square to be 36, but in this case I am assuming that sigma square is unknown and we are going to estimate it on the basis of given sample of data. So, we had 20 values on the day temperature in a particular city, and the temperature were assumed to follow a normal mu sigma square distribution, and these are the values of the sample in degrees Celsius that we had obtained. And yeah, means if you want to compute the confidence interval manually, I have computed here the mean of x, variance of x, which are coming out to be here 41.97 and 36.85 respectively, and the value of this t alpha by 2 n minus 1, which is here at say t 0.05 divided by 2 and with 20 minus 1, that is 19 degrees of freedom. You can see here I have computed here, and this is coming out to be 2.09. So, I have computed all these values separately in the R software, and this screenshot is given here that you can actually verify yourself. But my objective here is to put all these values in the expression and try to obtain these values manually, and then I will try to obtain the same values in the R software also. So, I try to substitute here the value of capital X bar, value of t, and value of s by root n here like this, and I obtain the value of this expression as 39.12. So, the lower confidence limit of mu in this case is coming out to be 39.12, and similarly you can compute the upper limit also just by replacing minus by plus sign, and this value is coming out to be 44.81, right. And you can see here this is sample mean whose value is 41.97. This is lying inside this interval, in fact in the mid of the interval, right. So, now I can say that with 95% confidence the true parameter mu is covered by this interval 39.12 to 44.81, right. So, you can see it is not difficult at all to compute such confidence interval even when sigma square is unknown to us, right. And if you want to find out the value of the sample size such that we are 95% confident that the absolute error x bar minus mu will not exceed say some value say 0.5, then we already have obtained the expression. You simply have to substitute the value of t, s and here e, and you can compute the value of here n, which is coming out to be here approximately 644. So, you can see here that this value has increased in comparison to the sample size that you had obtained in the earlier lecture when sigma square was assumed to be known. That is expected, means when you are trying to estimate something, then definitely you are going to increase the variability, and once you know something, that means there is no error into it, there is no randomness. Okay, now I try to do the same example in the R software, but let me be honest, here I am going to use a command which is related to the topic which I am going to cover in the forthcoming lecture. It is about test of hypothesis. Actually, this test of hypothesis and confidence interval estimation, they are interrelated, right. So, that is why I am just using here the command, I am giving you the command here, but when I will be considering the topic of t-test, then I will try to give you the complete detail of this R command. So, we are using here the command conf.int, which is confidence interval from the value of the t-test, right. And suppose we have given the data here as say here like this, suppose here x, and then you are simply try to write down here t dot test x, which is the data vector here, and confidence level, that is conf dot level is equal to 0.95, and then you have to write down here dollar and then conf dot int. So, this is here the value of 1 minus alpha, which is given by conf dot level. So, at the moment I would request you that you try to accept it as on the as a face value, and later on I will try to give you the entire results, right. And if you try to get this value, this will come out to be a 39.12 to 44.80, and this is the interval that you can obtain here. So, you can see here that it is not difficult at all to obtain such confidence interval, and this is here the screenshot. But now let me try to first show you these things on the R console. So, let me try to copy this data to save some time. You can see here, this is here the data, say I am calling it here as say x, just for the sake of simplicity, and then I try to use this command for obtaining the confidence interval, and you can see here this is coming out to be like this 39.123842 44.80616. So this is the 95% confidence, and these are the lower and upper limits of the confidence interval. Right, okay, so now after this we come back to our slide and we try to discuss one more topic. This is about the confidence interval estimation for the variance of a normal distribution. Right, you have two parameters in the normal distribution, mu and sigma square. So up to now you have only assumed that sigma square is known or unknown, and then you have tried to provide the confidence interval for the mean. But now we are assuming that sigma square is unknown, so we can estimate the sigma square through point estimate as well as through the confidence interval estimation. Right, so how to get it done, that is what I am going to now discuss here. So we have a random sample x1, x2, xn from normal mu sigma square, and where sigma square is unknown, and yeah, I am indicating the data vector here as say x underscore just for the sake of simplicity, and we know that in this case the mean and variance can be estimated by say sample mean and this quantity capital S square as we have done earlier, right. And now we have to create a pivotal quantity. So for that we are going to take the help of chi-square distribution and the topic that we already have understood actually. So we are going to use them. So we know that n minus 1 into S square upon sigma square follows a chi-square distribution with n minus 1 degrees of freedom. So now I can consider this quantity as pivotal quantity. Why? Because this is a quantity which is depending on the unknown parameter sigma square and x1, x2, xn through S square, but its distribution is independent of the unknown parameter, which is chi-square with only n minus 1 degrees of freedom. Right. So now I can use this statistics to construct the confidence interval. Remember one thing, that chi-square distribution is not a symmetric distribution. So you cannot use here like plus minus z alpha by 2 or plus minus t alpha by 2, right. You have to be careful. So actually this will look like this. So in case if you are trying to take here this area to be here alpha by 2, then this critical point is going to be chi-square alpha by 2 n minus 1, and then this area will become here like alpha by 2, but this point is going to be indicated by chi-square with 1 minus alpha by 2 and n minus 1 degrees of freedom, right. And this middle blue part will be 1 minus alpha, right. So always remember that this chi-square and even f, they are not the symmetric distribution, right. So now I use this statistics n minus 1 S square upon sigma square to find out the confidence interval. So I can say that this n minus 1 S square upon sigma square. So this is the curve of chi-square with n minus 1 degrees of freedom. This is actually n minus 1 into S square upon sigma square, right. So this is the curve of this quantity. So now this quantity is going to lie between these two values, you can see here this and here this. So that is what precisely I am going to write down here, that this quantity is lying between these two limits, chi-square value with 1 minus alpha by 2 and alpha by 2 and with n minus 1 degrees of freedom, right, as I shown you in the figure also. So now you can simply solve it, and then this sigma square will be lying between say n minus 1 S square divided by chi-square with alpha by 2 n minus 1 degrees of freedom and n minus 1 S square divided by chi-square 1 minus alpha by 2 and n minus 1 degrees of freedom, and the probability of this event is going to be exactly 1 minus alpha, right. So this chi-square alpha by 2 n minus 1 is the 100 alpha by 2 percent point on the chi-square distribution with n minus 1 degrees of freedom, that we know, right. So now I can write down here that the 101 minus alpha percent confidence interval for sigma square is obtained here like this. This is here the theta hat L, which is based on x1, x2, xn, and this is here theta hat u, which is again based on x1, x2, xn. And we have x1, x2, xn, so we can compute the value of capital S square, and then we can obtain the value of chi-square from the table or from the R software, and we can compute this interval, right. But you have to keep in mind that this 101 minus alpha percent confidence interval for sigma square is not the shortest length confidence interval, just like it was in the case of normal distribution where we tried to find the confidence interval of mean when sigma square is known and unknown, right. So this is what you have to keep in mind. Now the question here is how we can obtain this confidence interval in our software. Well, for that you have to use here a special package. This is ENVSTATS, and here this E and this S, they are in capital letters. You have to be careful. Right. So, this is a package in which some data sets of a book of environmental statistics is there. So, they have given this program to compute the confidence interval for sigma square. And let me be honest here that once again this command which we are going to use here for the construction of confidence interval, it is VARTEST, where T is going to be in the capital letter. Actually, this is for the chi-square test, which is the topic of test of hypothesis, which I am going to take up after this lecture, and it will come very soon before us. So, that is why I am unable to give you the complete details of this command, but here I would request you that you please accept it on the face value and use this command to construct the confidence interval for sigma square in the case of normal distribution. So, the command here is simple VARTEST, where this capital T is here, and then you have to give the data vector here x, and then you have to specify the confidence interval whatever you want, means the default here is 0.95, right. So, now in case if you try to see here that I try to take the same example that I just considered, that we have the 20 observation on the day temperature of our city in degrees Celsius, and we are assuming the population to be normal mu sigma square, and this is the data here, and we want to construct here a confidence interval for sigma square, and suppose just for the sake of illustration I am taking here the confidence interval to be 70% and 95%. You can see using the software it is very easy, right. Now, if I ask you to do it manually, you know that it is very simple now. Okay. So, this is here the data, and now I try to give this command over here, right, VARTEST on the data here temperature, and then the confidence level here is 0.70, that you can change according to your wish, right. Your outcome will look actually like this, but you have to concentrate only on this part which I have put inside a box, right. This is 70% confidence interval, and there are two values here like this. So, this is here the value of theta hat L, and this is the value of here theta hat U, that is the lower and upper bounds of the confidence interval of sigma square, right. Rest all these values whatever they are here, that I will try to explain you when I try to consider the topic of test of hypothesis. That is my promise to you, we are going to do it. Okay, now, if you try to change this confidence level from 0.70 to 0.95, you just use the same command over here, and then you will get here this confidence interval. But now, can you see what is really the difference between the two? Here the confidence interval is from 27 to 54. So, the length of the confidence interval is approximately 54 minus 27, which is equal to 27, and here in this case the confidence interval limits are 21 nearly and say 78 nearly approximately. So, the length of the confidence interval is approximately 78 minus 21. So, now you can see here this is greater than the length what you have obtained when your confidence level is 70%. So, now if you try to recall that in the last lecture when we introduced the concept of confidence interval, we had talked about it, right. So, these are outcomes of the same program, but now my choice will be that I try to show you these things on the R console. So, let us try to come to R console and try to do the same thing over here, right. So, let me try to first clear the screen, and let me try to enter the data and try to execute it. So, now I have entered here the data on the temperature. You can see here this is here like this, and now I try to compute the confidence interval. You can see here using this command at confidence level equal to 0.70, this is the outcome. So, you can see here these are the confidence limits, right. And similarly, if you try to change the confidence level to be, suppose here 90, you can see here these limits are going to change. So, you can see here that it is not difficult to compute this confidence limit on the basis of given sample of data. So, now with this illustration I come to an end to this lecture and also to the topic of confidence interval estimation. One thing I would like to clarify here, that we also have confidence interval for different parametric function, like if you have two populations and you want to construct the confidence interval for mu1 minus mu2, where mu1 and mu2 are the means of the two populations and so on. But in order to understand these things, I first need to explain you this type of requirement. And this type of requirement I am going to explain you when I try to take the, say, test of hypothesis. That is my next topic and possibly the last topic of this course. So, I am not covering those topics over here, but if you wish, if you know about this confidence interval, then you can go through the book. They are very simple and I will show you that they can be obtained exactly in the same way as you have done this confidence interval. Now, after this I have taken the example only for the normal distribution, but you can construct such confidence interval for any probability density function or probability mass function, right. But you have to be just be careful that when you are trying to deal with the discrete random variable, like as if you want to find out the confidence interval for a population proportion using the binomial distribution, then you have to take care of the continuity correction. And there is another thing, that in this case we were able to find out the pivotal quantity whose distribution is exact. But many times finding out the exact distribution may be difficult, then we try to use the standard normal curve after transforming the statistics, that x bar minus mu divided by sigma by root n type of transformation, and we try to compute the confidence interval based on that approximated normal 0 1 distribution. So, whatever concepts we have used, whatever things we have learned for such approximation, they have to be implemented here also, because you are simply trying to compute the probability. If you try to see, many times you have computed the probability that x is lying between, say, this x1 and x2, and you transformed it to a standard normal variate, and then you computed the probability using the normal 0 1 distribution. So, the type of calculation what you have done in the confidence interval estimation, they are the same. So, whatever knowledge you have learned, you have gained while doing those exercises, that is going to be used here also. I do not need to repeat it again and again, right. So, now I will request you that you try to take some examples from the book, try to solve them, try to practice them, and try to see how you can employ them in the R software. Now, you can see here that the use of the software will come only when you know what has to be done and what is the correct expression, what is the correct tool that has to be employed to get the correct answer of a problem. So, that is why this theory is very important. That is gives you the basic fundamental by which you can decide what exactly you want to do. Now, once you decide that this is what I want, now there will be challenges in the data science, that if the data is too big, how are you going to handle it, and those types of complications. For that we need the help of computer scientists also. So, I would request you, you try to revise this lecture, try to compute confidence interval for some other type of distributions also, and I will see you in the next lecture with a new topic. Till then, goodbye.